minus, yeah, exactly. So no kinetic energy. So when it has no kinetic energy, the thermometer should show the lowest possible temperature. Now, if you use degrees Celsius, right? Eta ধর হচ্ছে 40 degrees Celsius. This is 100 degrees Celsius. And when there's no Ke, what should that be? Minus 273.15 degrees Celsius. And this 0.15 is needed in your A levels. Okay. So A levels, when you do your math, they expect you to use the 5 decimal place value or 5 significant figure. So that's the lowest temperature possible. But it's not really intuitive, because when I want 0 Ke, I would prefer an answer to be 0. Like no Ke, no temperature, right? And that's when we realize that this degree Celsius is not really a good scale. We should rather use what? Kelvin, okay? And in Kelvin scale, when there's no Ke, what is the value? 0 Kelvin, okay? And this is going to be 313 Kelvin. And this one is 373 Kelvin. So yeah, these are what temperatures mean. Temperatures are basically a measure of how much Ke an object has, and the temperature scale that directly reflects the Ke amount is Kelvin scale. Okay, do you understand? So my thermometer here can show the rise in Ke, but it doesn't tell me the amount of Ke. Do you understand the difference within what that means? So when there's an increase here, right, value, I know that Ke increase. That's like, you know, confirmed. But when this is 0 here, does it actually mean the Ke is 0? No. Why? Because this scale that's been used here doesn't completely reflect Ke. And what's the scale that reflects Ke? The Kelvin scale. Okay. So yeah, that's the summary before we start. So you can just set the definition at Kirachi, which is what does temperature mean? Okay. So temperature, this is definition, is the measure of the average kinetic energy of the particles in a substance, or direct relationship between temperature and energy. We use the Kelvin scale. 0 Kelvin indicates that the material has no magnetism. My duty teacher na duty teacher. Acha, there are two definitions. Eta boleo chole, they'll like accept this, or they'll also accept that. They're very similar. Measure of how hot or cold an object is, and is further based on the amount of internal energy an object possesses. Internal energy of an object is basically a K that it has. Okay, so both of these are similar. Celsius. So Celsius scale is thermometer scale based on the temperatures of water. So do you know how thermometer scales are made? So if you want to make a thermometer scale, right, you have to use a liquid, and you choose the boiling point of the liquid as 100, and you consider the freezing point of the liquid as 0. So for Celsius scale, they use water as reference. So 0 degrees Celsius is when water freezes, and 100 degrees Celsius is when water boils, right? It's not a coincidence that 0 day freeze per 100 day boil for it. It's like that because we use water as a reference. If you use Fahrenheit scale, you'll find the answers are strange, right? But 0 Fahrenheit is when alcohol freezes, and 100 Fahrenheit is when alcohol boils. So Fahrenheit scale is based on what? Alcohol. So whenever you want to make a thermometer scale, right, what you need to do is you need to choose a liquid, and you find its boiling point and melting point, and use those, that lower fixed point, upper fixed point, and that's how you make a scale. This was done originally, right? But later on, we realized that there's a limit till which you can use these scales, because 0 is freezing point, but that's not the lowest temperature out there. So eventually they started investigating, and they found that if you use the kinetic energy of particles as your scale, right, you get the absolute temperature. That's what's called the absolute scale. So where your 0 would actually mean the particle has 0 K, and there's no upper bound. You can go as high as you want. Okay, so let's move on. So what we're going to learn today is the process of thermal equilibrium, right? So what thermal equilibrium means, last class of Old Hey, you have a cup here, and I hold this cup right now. It's much hotter than my hand, right? And I can feel it's warm. But then what I do is I take my hand away, and if I touch my hand with the other hand, I can feel that this is hot. So somehow energy got transferred from the cup to my hand, because my hand is warmer right now. So the question is, why did the energy come to my hand, and what was the process, right? And why didn't the energy go the other way? So can we make it go the other way? So to answer those questions, we need to understand, how does energy transfer actually take place? So if you have two objects, okay? And this is where we start our chapter, by the way. So let's say you have two objects identical in shape and mass and everything, material as well. Shobdik identical, otherwise this demonstration doesn't work. So let's say I have this object here, very low temperature, 10 degrees Celsius, okay, compared to what we normally know. And I take another object, identical in every manner, okay, which is much warmer, and this is 90 degrees Celsius. And what I do is I bring these two objects and put them next to each other like that. Now, when they're in contact, and you learn this in O levels with conduction, right? Energy will be transferred from one place to another by means of contact, right? So what will happen is, when you look in the molecular level, you'll find that in this particular object, there are a lot of particles here that have more Ke, like high Ke, and on this side you'll find particles that have on average what Ke, low Ke. However, something you need to understand, on the right hand side, I do have particles that have what Ke, low Ke. Similarly, on the left hand side, I do have particles that have what Ke, high Ke. This is the concept of average kinetic energy distribution, that whenever you take a sample, you will find almost all types of Ke out there, but a certain amount of Ke will be higher, and that constitutes what your Ke is, okay? So in this room, for example, if I want to find the Ke of the particles in this room, right, you will have particles in this room that have Ke, next to absolute 0. And the particle is lying on the floor right now, no energy, right? Also, you'll have particles here that have enough Ke to be on the sun. But on average, what energy do they have? Whatever you experience right now, okay? So that's the concept of average kinetic energy. Anyways, so when you have this here, what happens is energy transfer takes place. And the energy would be transferred always from higher Ke to lower Ke. So what's happening here is that energy is transferred from these high Ke particles to the low Ke particles. But aren't there a few particles here which are higher Ke as well? So they'll also transfer energy which way? The other way. But turns out, because there are more Ke particles with higher energy on the right-hand side, the amount of energy transfer will be more, net energy transfer would be more from the right to the left. So you'll have, let's say, 3 arrows of energy transfer taking place here for one energy transfer taking place there. So which way is the net energy transfer taking place? Yeah, from right to left, right? So overall, what will happen over time, you'll start to notice there are more, what happened in here, higher Ke particles arriving, right? So I'll draw this niche. Yeah, so what will happen is you'll start to notice there are more higher Ke particles showing up here. Can you tell me what's the consequence of that on my temperature reading? আজকে তো শিখলাম that temperature is a measure of how much Ke you have, right? And I'm now seeing that there are more Ke particles showing up here because of the transfer process, right? What would you expect this value to do? Increase, right? So you'll start to notice this is getting warmer. So let's say it becomes 40, right? And on the other side, you'll start to notice this number here, কি করা start করছে? Yeah, it decreases because the kinetic energy on the right hand side is actually now becoming less. So you have more cooler particles showing up here. So this will also go down. Now the question is by how much? If you use identical mass, right, same material, same size of contact and everything, the amount by which this increases must be exactly the same by which that decreases. Why? Aren't the kinetic energy of these particles transferred to that side? So if they're equal in concentration, size, and everything, if 5 decreases here, 5 increases there, right? So এখানে যদি এটা 40 হয়, how much is the rise here? 30 degrees Celsius. How much should the fall there be? Yeah, so এটা কমে হচ্ছে কত হবে এখানে? 60. And this is when you have higher temperature, lower temperature here, right? Lower than before. But do you think energy transfer will still take place, or will it stop now? It'll still take place because on average, this still has more Ke, right? But the problem is the rate will fall because there's something that we need to learn called the temperature gradient, okay? So what is this temperature gradient here? So imagine a flat line like that, okay? And these sides are temperature values. So this side is like 0 right now, that side is also 0. What I do is I hold it like that, let's say, so that this is now 90, right? The target question is 90 and 10. Do you see the slope here? So if you release a ball here, how would the ball go? Down the slope like that. Now, if I reduce the difference, there's still a gradient, right? And I release the ball. Do you think the ball will move as fast or slow? Slow, right? So because it takes longer, right? And if you go even closer to the temperatures to each other, the rate decreases. And the moment they're same, what's the flow? It doesn't happen anymore, right? That's called a temperature gradient. So temperature gradient essentially tells you the bigger the difference in temperature, the faster the rate of flow, because there are more particles available to lose energy. But once you are at similar temperature, why does it become slow? So let's say I have these at similar temperature, right? Why are they becoming slow? The rate of transfer. So let's say they're nearly equal. But why nearly equal makes it a slow process? So let's say this is 44 degrees Celsius and this is 46 degrees Celsius, right? Why is the process going to take awfully long for them to become equal? They're far and few, so it takes longer for them to transfer their energy. Yes, so what happened is, once the temperature becomes very similar, if you look at the Ke transfer, right, you'll find that the amount of red particles here, and I'll clean this side as well, the amount of red particles on that side, ki hobe? Same. Do you agree? Why same? Because aren't the temperatures very similar? But here, 1 or 2 particles have more energy. So I'll use a deeper red color, like this particle. It actually has more energy compared to the left-hand side. Transfer kore, edike transfer kore, odike transfer kore. Eventually, for this energy to reach the other side will take a lot of time. Previously, why didn't it take time? Because all the high energy particles were readily available here. They were all over the place here. So right away, you could have the transfer take place. But once it starts to, give out the energy, those high energy particles are very far and few. So for them to transfer the energy, it requires a lot of time. And it's also the similar case you have with evaporation. Remember, the energetic particles escape, right? And they're found at the surface. So if you have a container that's very small in size, is evaporation fast or slow? Slow, right? Why is that so? Yeah, because those high energetic particles are not being exposed properly. But if you pour that water on a table, and let's say the table is now fully soaked, right? Doesn't it dry right away? Why is that so? Because you're exposing them very easily. So ekhane jeta hocche, this is not exposed yet to that material, right? So eventually, over time, some energy transfer here, there, conduction hocche, right? So eventually, the energy transfer will take place, and at one point, the system will reach what we call thermal equilibrium. So let's see what thermal equilibrium is. Thermal equilibrium is when both my materials here have what temperature? Same temperature. So in this case, this is going to be 50 degrees Celsius, and this is going to be 50 degrees Celsius. Can 50 degrees Celsius? Let me explain. So we started with a temperature of how much here? 90 and 10, right? The midpoint would be what of these two? Average, right? So what's the average of 90 and 10? 50, which means this temperature goes up by 40. This temperature goes down by how much? 40. And shouldn't the change be equal? Because if this loses 10 Ke, shouldn't that gain the same amount of Ke, right? So as a result, if the temperature falls on this side, temperature would rise on that side by same amount. And at one point, what will happen is that the system is said to have reached equilibrium. Now, something interesting happens during equilibrium, which is energy transfer is still taking place. But by what amount on both sides? Equal amount, because there's an idea out there that energy transfer never stops. It will always happen. It will always continue. It's a flow. It's a motion that will always take place. But when you have two objects with same energy, right? What happens to the net flow of energy? It's zero. Okay. So energy in the সারাক্ষণ flow করে বেড়াচ্ছে. It's moving like that, like that, like that. It's always in the move, right? As it's on the move, it's gaining, losing, gaining, losing, gaining, losing. But if you have same temperatures on both sides, right, the gain and the loss is generally the same. So as a result, there's no net change in energy. Okay. But this is all based on, one of you had a question that none of the energy is lost to the surrounding. Because if they're lost to the surrounding, the system is the surrounding, and wouldn't energy go to the surrounding as well, right? So we are ignoring that. But just generally understand that if I have this cup here and I keep it here, it's getting cold over time. Where's the energy going? Yeah, to the air around it. Okay. So yeah, that's the process. So this is when it reaches thermal equilibrium. So what you see here is thermal equilibrium. So what's the definition of thermal equilibrium? Thermal equilibrium is a state that is attained when two objects have same temperature, and hence there is no net transfer of kinetic energy or energy. Okay, so when two objects have the same temperature, the energy transfer stops, and that's called thermal equilibrium. So one thing that you have to be careful about for thermal equilibrium, do you need two objects to have same energy, or do you need two objects to have same temperature? So it's an important point. Okay, so what do you wait for to equate to know that the system has attained thermal equilibrium? Now, আমি যখন thermal equilibrium reach হচ্ছে না কি না কেমনে বুঝবো? Do I wait for the energies to become equal, or do I wait for the temperature to become equal? Keep in mind, both might not become equal. So it's not just temperature equal to the energy equal with not necessary. Okay, so which one is the factor that we look for to know if a system is in equilibrium? Temperature. Okay, and it had too complicated. I kept saying they're identical, right? I'll now explain why the process is complicated. But we need more math to do that, and that's why we have this chapter right now, because what I said so far is actually O-level stuff. There's nothing new that I've mentioned yet. But look at this. Let's say you have a swimming pool here, and the swimming pool has a temperature of 20 degrees Celsius. Okay, so that's 20 degrees Celsius. And what you do is you take a cup of water, cup of boiling water, okay, very high temperature water. And what you do is you pour that water into the swimming pool. So this is the high temperature water, and I pour it into the swimming pool. What's the temperature of my water here? 100 degrees Celsius, okay? And what's the temperature of the swimming pool? 20 degrees Celsius. Now, if they want to attain thermal equilibrium, they must come to a midpoint, right? What should the temperature be when the midpoint is attained between these two numbers, 100 and 120? 60 degrees Celsius, right? The 100 will go down by 40, and the 20 will go up by how much? 40 as well, right? But do you think that happens? No, right? Because if you pour water here into the swimming pool like that, you'll find that there's almost no change to the swimming pool. So do you see that it's not necessary that the temperature will attain a equilibrium? There's another very important factor that plays a role here. What is it? Mass of the water. Okay, Tajna, our previous example, what did I say were the two blocks identical? What if they're not identical? How do you know when they reach thermal equilibrium, and how do you know what thermal equilibrium do they reach? For that, we had a math in O levels. Does anyone remember that? Yeah, the Q equals to MC del T. Remember that formula? So you find the amount of energy taken in by the water and the amount of energy given out by the glass of water, and then you find the answer. Okay, so my point that I'm trying to make here is thermal equilibrium doesn't necessarily mean the average temperature. It does mean they both will eventually have what temperature? Same temperature. So how is it same temperature? I'll explain. This 100 degrees Celsius here, right? Once you pour it into the swimming pool, let's say here, and let's say the water is there. I use colored water, so I know where it went, right? How the temperature of this colored part compared to the temperature of the swimming pool? They should be same. How is it possible? This temperature will actually rise because aren't you providing some energy? But the rise will be something like this, 20.0001 degrees Celsius. And this 100 degrees Celsius will actually fall. And it'll fall to what temperature as well? 20.0001 degrees Celsius. And that's how it reaches thermal equilibrium. So the water that's here will actually lose more temperature, and the water that's here will actually gain less temperature. But how much energy that the water lost here and how much energy the water gained here must be same. At the end of the day, what conservation is there? Is there a law of conservation of temperature, or is there a law of conservation of energy? Energy, right? So this water that you see here is going to lose energy. The boiling water loses energy lost. And this water that you see here will gain energy gain. But that 1 cup of water doesn't have enough energy for the whole swimming pool to heat up. That's why it doesn't change. Okay, so if I use a bigger bucket of water, would you expect more rise in temperature? Yes, because you're providing more energy. What if I take like a truckload of water? Obviously, that'll be more observable, right? And when you have equal amounts of water, that becomes much easier. When you have more water, that's warmer, it becomes way easier. Okay, so if I want to heat up a bucket of water, right, like it's room temperature, I'm taking what do I do? I'll take boiling water and just pour it into it. But if I take like a dropper full of boiling water, does it work? No, right? Because it doesn't have enough energy. That's the main part. Okay, so yeah, this is called thermal equilibrium. I'll just summarize what's going on here first of all. So in the first scenario, what is taking place here? Energy transfer by means of conduction. And the energy transfer always takes place from where? Always from higher temperature to lower temperature. Yes. At the bottom of the ocean. Oh, that's to do with the density. So all the oceans in the world, right? At the bottom, do you know what the temperature is? 4 degrees Celsius. Every ocean, every water body ever, right? If you go to the bottom, you'll find the temperature is 4 degrees Celsius. Yes. So why? You guys didn't learn it? Chemistry test. So do you guys learn the anomalous expansion of water? No? Okay, nice. The fact that water has a very strange behavior. Ice floats. Huh? Yeah. So it's called what? The peculiar properties of water. Okay. It's anomalous expansion of water. So water has this very strange behavior. You know that more dense materials are, right? They're supposed to sink. Water, the more dense it becomes, it floats. And you'll find that ice floats. Ice is solid, right? Why would solid float? Shouldn't solid sink? So water has a strange behavior where it becomes solid and then it actually becomes less dense, right? And it becomes liquid, it actually becomes more dense. And the most dense liquid is at 4 degrees Celsius. That I think you guys probably don't know. 4 degrees Celsius. So 4 degrees Celsius. So if you go to the oceans of any place, like any water body, if you go to the bottom of it, right, it's always 4 degrees Celsius. And it's the mystery that solves the fact that when oceans freeze, lakes freeze, right, fish don't die. So if you go to lakes that are frozen, right, you'll find the surface is frozen. The fish survive for very properly, no problem there. Why? Because right at the bottom of that lake was the temperature. 4, but then they can survive 4 degrees Celsius, right? So it's due to anomalous expansion of water. Okay, so that's the reason why at the bottom it's always a different temperature, a lower temperature compared to the rest, 4 degrees Celsius. Always from higher temperature to lower temperature. That's why they believe like the water bodies of Europa, there's the moon of Jupiter, it has water in it. So that's frozen. But they know that it can't be frozen entirely because right at the bottom of that water as well, what should the temperature be? Yeah, so it means there's liquid water out there. So there's a possibility that there could be life there as well. Hard water monitor is just the seawater. Huh. No, the hard water and soft water. Hard water is the one that has ions involved in it. Heavy water, heavy water is different, right? Hard water is seawater. All right. So always from higher temperature to lower temperature. তারপর হচ্ছে এখানে হচ্ছে as temperature difference decreases, the transfer rate decreases. Okay. Our thermal equilibrium কি হচ্ছে no net energy transfer. Common mistake is students will say no energy transfer. That's not true. Okay, there is energy transfer. There's no net energy transfer. Right, so that's it. And Jab mentioned column so far, it's written on the right. So if you want, you can copy that. When two objects are in contact, energy transfer takes place from an object with higher temperature to a body with lower temperature. The net energy flow takes place until the systems are at the same temperature. This is known as thermal equilibrium. Okay, and it is important to note that thermal equilibrium is attained, the energy flow still takes place, but there is no net energy flow. This is because there will always be particles that are at different energy levels due to random distribution. So you will always have one particle that's more energetic here and less there. So eventually energy transfer will take place. And the idea of temperature gradient of Boleraki, it's helpful to know. Temperature gradient. What is temperature gradient? Higher the temperature difference, higher the rate of flow. Wait, the paper 5 project. Paper 5 checklist. That's planning question. Paper 5 question 1. But there's a small problem. I can give you that. So when there's data parts of paper 5, paper 5 has a lot of questions based on oscillations, based on capacitors, based on chapters that are end chapters. How are you doing that? On the mechanics based in the paper 5 plan, we call it's mostly based on magnetism, based on capacitors, based on thermal physics. So a transformer. So transform to magnetism. হ্যাঁ, এখানে এই পেপার ফাইবার হচ্ছে মেইন থিং হচ্ছে সামথিং কল লিনিয়ার লগ। লিনিয়ার লগ যদি বুঝো তাহলে পেপার ফাইভ গুলোর এই প্ল্যানিং গুলো করতে পারবা। সো দোল গিভ ইউ ভেরি কমপ্লিকেটেড ইকুয়েশনস। চেক করে দেখবো যে পেপার ফাইভের প্ল্যানিং এর একটা ইকুয়েশন দেয় ওরা, সুপার কমপ্লিকেটেড, মানে there will be like 5 6 variables and they'll ask you to plan an experiment between two of them, right? And then last দেখবা যে এই জায়গায় সবচেয়ে বেশি মার্ক থাকে is to draw a graph, and graph থেকে হচ্ছে gradient বের করতে হবে, বা what does the y-intercept give you. So the challenge is to convert their equations to a straight line. And ওটার জন্য there's a mathematical model called a linear log. Do you know linear log? No, question 1. Question 2 তো হচ্ছিল graph. হ্যাঁ, but question 1 এর যখন প্ল্যানিং করতেছো তোমাকে একটা এক্সপেরিমেন্ট ডিজাইন করতে হবে, রাইট? What's your independent variable? What's the dependent variable? How do you find the constant from the graph? এগুলা তো হচ্ছে the main part. তো এই গ্রাফটা তো একটা ইকুয়েশন ডিরাইভ করতে হবে। ওই ইকুয়েশনটা ডিরাইভ করার জন্য there's something called linear log. Linear log অ্যাপ্লাই করতে হয়। So linear log um, linear log is the idea that you can convert any graph into a straight line. You have it, right? Yeah, I know Cambridge students থাকে, এটা যেমন থাকে না, আমার শিখাতে হয়। তোমাদের কোন ক্লাসে ছিল? A2-তে ম্যাথে? আচ্ছা, তোমরা আচ্ছা আচ্ছা, রাইট। হ্যাঁ, তো লিনিয়ার লগ যদি পারো তাহলে দেখবা these questions are easier to design, because তোমাকে ইকুয়েশনটা ডিরাইভ না করলে you wouldn't know how to design your experiment. Yeah, so তোমার ধরো হচ্ছে a to the power x equals to c, so you take log something on log something, and then you'll eventually get a straight line. Okay, so if any question, let me know. This is thermal equilibrium. বলো। এই যে ফার্স্ট এটা সিম্পলটা। হ্যাঁ, so এখানে দেখো আমার when I placed two objects next to each other, the temperature went up, the temperature went down, and they became equal, right? At the midpoint. So এই যে 90 plus 10 এর midpoint কত? 100 or half 50, right? But the thing is, it's not always going to be the midpoint where they attain equilibrium. Why is that so? It's because, swimming pool example, the swimming pool has water at 20 degrees Celsius, you pour 100 degrees Celsius. What do you need to do to the swimming pool so that temperature rises? You have to increase the energy of every molecule in the swimming pool so that on average the K increases, right? Does a glass of water have enough energy for it to be done? No, right? So when you pour the glass of water here, the energy বাড়বে, ওটার জন্য temperature খুবই অল্প বাড়বে, and when it reaches equilibrium, it's not going to be a midpoint, it's somewhere else. So the factor that plays a very important role in the value of the equilibrium temperature is the mass. এখানে কেন it wasn't a problem? Because I used what mass? Equal mass. So equal mass, it's not a problem, but when you have unequal mass, the mass plays a role, and that role we'll see how to solve. Done? Okay, let's so that's the chapter, by the way. Every class will be doing one topic, because look at this, it's just 2 points here. Okay, so we're done with thermal equilibrium. এখানে একটা summary আছে, summary একটু দেখি। Look at this. Energy is always transferred from a hotter object to a cooler object. It's the concept of natural flow. So diffusion, osmosis, temperature transfer, voltage, current flow, always from higher potential to lower potential, higher value to lower value, right? So that is it. But there's a place where energy goes the other way, from lower value to higher value. Can you give me an example? AC, active transport to biology. Actually very similar. It's called a heat engine and heat pump. So heat pump হচ্ছে, AC টা actually, AC also কাজ করে is a refrigerator. So the refrigerator is how it does the reverse, right? Because it takes the energy from the food, which is warmer, and takes it out. And where does it take it out? On the back is a heat pump. If you put your hand in the back of the refrigerator, you'll find it's warm, and the warmth is actually coming from the food. And then the food's energy has been removed. How has it been removed? So they use a gas inside the refrigerator. It's called Freon. Freon এখন use করে না, they use different gases. They use it for your AC as well. Sometimes they'll come and like refill the gas in your AC, right? Refrigerant gas বলা হয়. That gas has a property when it's very cool that when you pass it over anything, right, it instantly absorbs the energy from that object. it has a very low specific heat capacity. Remember specific capacity? So when the object, the gas flows over it, right, it takes the energy away and it's pumped to the backside. And as it goes to the backside, the energy is removed from it, from the gas. And what does the gas become in the process? Cooler. And it comes back here. How is that done? Very complicated mechanical process. It compresses the gas. That's the name for the machine that does it. It's called a compressor. The AC compressor it just stops working, just hot air coming out of it, right? That compression process is what pushes the hot air or the heat out of the gas, right? And then it comes back in and it keeps doing that. And to compress that gas, you need electricity. And that's why refrigerators are very efficient, even ACs actually. Why? Because once your room is very cold, that gas that's transferred, right, doesn't actually change too much in energy. So it's just maintaining the temperature. The most amount of energy your refrigerator uses is when? The first day you buy it. Continuing first can show, within puroটা ঠান্ডা করতে সবচেয়ে বেশি time লাগে. You'll even know that they'll say don't use it for a day, let it cool down. And then once you keep your food inside, right, it uses energy similar to a couple of tube lights. I know it feels like AC refrigerator it should consume a lot of electricity, right? To maintain it doesn't. To cool down it does a lot. Okay. So if you keep your AC on for throughout the day, right, in your house, technically it should actually give you a lower bill compared to turning it on and off and on and off. Because every time you turn it off, and when you turn it back on, it has to do a lot of work to take the heat out. But if you can maintain a temperature, it will actually not cost you as much. Okay. Right. So what is the next one here? The two substances in physical contact to each other no longer exchange any heat and both reach equal temperature. So this is it, 100 to 0. This will only happen if they have what temperature or what mass? Equal masses, okay? The hotter region will cool down and the cooler region will heat up until they have same temperature. But this is not as straightforward as this. A last point I'm going to notice. What if you're heating the object and it starts to melt? Right? It can melt, like let's say ice cube. Things get complicated. And that kind of complexity is what we have in our AQ. So we have latent fusion, vaporization, everything. So eventually the math that we have, they do get very elaborate. The biggest math I've seen is 6 mark sector math. Okay. So they'll take like 2 objects, mix them, different material, different mass, different temperature. So everything is different about them. Where do they reach equilibrium? Find it. Okay, you get my point. So I mean, swimming it was pretty easy because it's water to water. But let's say what if you take an oil and another oil of more mass, less mass, high temperature, low temperature, and you mix them. What's the final temperature going to be? No, a different oil though. So eventually, once you start, they're not immiscible. They can mix. So as they mix and they eventually become a mixture, right? What's the final temperature? That's the ultimate math we have. Okay, so we are building towards that right now. Okay. Or then they'll act like 2 boxes. It'll still work. It's just like, there'll be 2 layers. There's a hot oil on the top and a cooler oil at the bottom. So that loses energy, this gains energy. And what she asked is actually interesting. So what if they're not miscible, right? And the temperatures are different? What will happen? So I take two oils, right? Like a hot oil, like the cold oil. And the hot oil is at the top and the cold oil is at the bottom, right? They're not mixing. They're 2 separate layers. Wouldn't energy transfer take place by conduction? So conduction will happen, right? So the liquid at the bottom will start to heat up and the liquid at the top will start to cool down. What would you observe? They'll start to? No, they're immiscible. They can't mix. The top one will start to go down and the lower one will start to go up, right? Yes, it's a lava lamp. Do you know what a lava lamp is? Oh, it's a lava lamp. Lava lamp is basically somebody did that experiment and came up with this. You've definitely seen it. Lava lamp. ভিতরে হচ্ছে দেখবা যে একটা বল থাকে, বলটা উপর নিচে যেতে থাকে. So these are 2 immiscible liquids, right? And one of them is low density, the other is high density. But as it cools down, it goes up, and there's a heater that heats it back, right? So it continuously just keeps moving up and down. What's the process that causes them to move up and down? Change in density. Low density rises up, cools down, falls back again. And being immiscible, you can actually see that process take place. Okay. Convection is not related, right? Because low density will cause it to rise up. Okay, let's move on to the next topic. এটাতে যাই। এটা হচ্ছে you'll notice the number is a little odd here. Look at the number here, 16. Okay, I've jumped to chapter 16 from 14. I'll tell you a reason behind it. This concept of internal energy is more important for thermodynamics than J chapter used for it. They use it in ideal gases, so I have to teach it here. That's and I think it's better if you learn it here. খুবই ইন্টারেস্টিং একটা টপিক, সবাই স্ক্রিনে দেখো। Let's start. So the topic deals with what is the combination of energies that you have for particles in an object. So if I take an object and if I want to see how the particles, what kind of energy do they have, that energy is called internal energy. Internal meaning the particles' actual energy inside, right? So O-level question, can you tell me what kind of energy do the particles have? What are particles doing generally speaking? Vibrate. So this is solid, okay? So what are the particles doing? Yeah, vibrating to and fro about fixed position, right? So like that. So these particles are vibrating. Is there any movement? Like movement from location to location? No, right? By the way, movement is a little deceiving. If I say particles are moving or not, vibration is also movement, right? So if they move from one location to another location, there's a term used in physics, translation or displacement, but translation is the right term. Translation, do you understand what it means? The particle actually goes somewhere, right? So in this particular case, the particles are vibrating about their fixed position, so there's movement. Now, if I move from this to a liquid state, right? What's the difference in structure? Yeah, so actually it's the same. And then you should know this, that liquids and solids under a microscope appear exactly the same. The difference is that there's a small gap available here like that. And that gap can allow some of the particles to what? Slip and slide and move like that and move like this. But in terms of spacing, they're actually very similar to what? Solid. And there's a practical evidence for that to show that solids and liquids have very limited spacing. Do you remember that experiment? You take a syringe, right? Fill it up with water and you plug the other end, right? And you press the syringe down, like, to close it. It's almost impossible. It barely goes in, right? But you say liquids have intermolecular spacing, which is more than solid, right? Where is that spacing? But if you replace a liquid with a gas, right? How far can you go in? A lot, right? And that shows you there's a lot of spacing out there. So eventually we found that solids and liquids, in terms of spacing, they're 80% similar. If solid spacing is X, liquid spacing would be 0.8X. It's very similar. Then what's the difference between a solid and a liquid? It's that missing molecule or gap that allows the molecules to walk over each other, slip and slide over each other, right? And as they slip and slide over each other, they can move around. So I'll show you how I can take this particle here, highlight to the other end of the setup. So what will I do? So there's actually a game like this. You know that puzzle where one piece is missing and you can move it around and take it anywhere? So you can actually take any molecule anywhere. And that is the property that gives the liquid its feature? Flow. So it can flow because of that. But because it's still very rigid, it takes the shape of the container you provide. Not like gas where it just flies around, right? So this is liquid. So liquid A, what are the particles doing? They're still vibrating, right? But isn't there a particle that's moving around? So they also have particles that contain what energy? Kinetic energy in terms of movement, right? So I'll put an arrow here. So that's what liquid particles do. They can actually move and they're also simultaneously what? Vibrating, which solid the movement bole kichu nai. So that's why it doesn't flow. Now let's look at gas molecules. How would gas molecules look like? Yes, so you'll have one particle here and another particle there, like that. And vibration bole kichu nai there. They only have one thing. What is it? Yeah, translation. And at what rate? Extremely high velocities. Okay, so you'll find the particles are moving like really fast. Okay, so yeah, sliding puzzle, you're right. So that's how the particles are. But there's one other property that we have not accounted for yet. Could be important. Solid liquid particles not only vibrate, not only move, they also spin, rotate, and that is a kinetic energy as well. So kinetic energy can come in three forms. One is called vibrational, that is this, oscillate, that's kinetic energy. The other one is rotational, and rotational example of just spinning top. A spinning top goes nowhere, but doesn't it have a lot of energy in it? It's called rotational kinetic energy. And the other one, the one that you know, is when it changes from position A to position B. What do you call that? Just translational kinetic energy. So when we say that a solid object has kinetic energy in it, right? It's actually a combination of what? All three, in this case, একটা থাকবে না solid-এর মধ্যে, translational. What is it mainly for a solid? Vibrational and rotational, right? Liquids-এর মধ্যে, you have vibrational, you have rotational, and you have what as well? Translational. Our gases-এর মধ্যে, there is no rotation. There is absolutely no scope of vibration. There's only one thing, translation. And in our gas laws, we make an assumption in a chapter called the ideal gas, where we assume our gas particles only have what? Translational K. So baki energy gulo amra ignore kori. Okay? And this is what your internal energy should be. But then we find that there's another energy involved here. So in rotation, just particles are rotating here. Why can't gas particles spin? Oh, they do. But the thing is that we make an assumption that the amount of spin energy they have is so negligible that compared to the translational value, it is non-existent. So imagine there's an asteroid crashing towards the Earth, right? It has mainly what energy? Translational K. Isn't the asteroid also like slightly rotating? Does that bother you? I mean, no one even cares about that, right? In terms of math, there's nothing that it has an impact on you, right? So you can completely ignore that. Same with gases as well. Asha, let's talk about the other energy, the one that actually keeps everything together. So what's preventing my molecules from vibrating and dislodging? Like chole jacche na keno? Something is bringing them back in, right? What is it? Yeah, the bonds, the chemical bonds, right? And those bonds are referred as potential energy. And we can picture the bonds very easily. Just imagine the bonds as very small springs. So imagine there's a spring between two particles, right? So as the particles are moving back and forth, aren't the springs expanding and collapsing? And as the spring expands, what kind of energy is stored? Elastic potential energy. It collapses, it becomes what? K, and then bounces back because of repulsion. Again, what does it become? EP, K, EP. So there's a energy stored in the bonds here. Bonds gulo ekhane eshe weaker hoye jabe because the particles are a little further apart, right? So it's a little weaker here. But the bonds are still there. It's called potential energy. And what about the bonds here between these two? Yes, and it's a very important assumption. Gases don't have any potential energy. The particles are so far apart, right? There's no actual attraction between them. So that's an assumption we make. Obviously, there has to be some attraction, but we assume it to be very negligible. So eventually, I mean, but eventually, internal energy, which is provided by the symbol U, is equal to what? The sum of all what? K plus, what is it? The potential energy. Now, why do we put the sum of all K? Because what are the different Ks that we have? Rotational, vibrational, and translational. This together is what your internal energy is. So if I want to know the internal energy of the cup here, I need to find the watt of the particles here. Every single particle is K and the potential between them and add them up. And that's going to have the final value. Okay, so we'll learn how to deal with that later. Why do they spin? Oh, because particles naturally they have an axis of rotation because of magnetic field around them. So they're always spinning. Right, so something like that, something like this. And the spin is the reason for north and south pole in iron. That's where the magnetism comes from. It forms a dipole.